everybody. I am back. Let me hit buttons here. There we go. Okay. Welcome back to Chem 121. It is Monday, week 8. There's a cat sitting here. Are you there? Yeah, you're there. Hold on. I gotta pull the chair over. Here you go. Say hi. Say hi. Say hi. There we go. Okay, great. Maya says hi. Okay, we'll shove her away. Here you go. She finally found this chair that's sitting in here and is sitting on it, and I'm just rolling her around. What do we have on the agenda? There's a quiz due. Is this today? Yeah, today's Monday. Yeah, tonight. So quiz number 6 is due tonight. Make sure you get that in by the deadline. That is a soft deadline. You have one more day to do it if you need to. Lab number 4 is going to go out this week. We'll probably talk about that either tomorrow or Wednesday. I think I mentioned last week that I'd like to use tomorrow as a lecture day. We'll see how far we get through this. I expect that I will probably still need to do that, but I guess we'll see based on how much material we finish. We finished last week by talking about gas laws, and we ended with this slide, I believe, where we talked about changes of state and how the outer ring of phases are changes that require energy to be put in. Oh, excuse me. Those changes of state we called endothermic. Endothermic meaning energy goes in. The ones on the inside of the little diagram there were phase changes where energy had to be removed or released or dissipated. We called those exothermic. Energy goes out. And that should be on the next slide here. So if we ask ourselves which states require energy and which release energy, so the ones that are endothermic, which require energy, are things like melting, boiling, and sublimation. When we put energy into these, the phase moves from a phase where the molecules don't move very much at all to a phase where the molecules move much more quickly. So that would be from solid to liquid, liquid to gas, or solid to gas. For the exothermic ones, that's just all the other ones. So we've got freezing. We've got condensate. Oh, I spelled boiling wrong. Ha ha ha. Boiling. Condensation. And deposition. So freezing is just the opposite. And so in order to get to those states where the molecules move less freely, we have to take away their kinetic energy somehow. And so we do that by removing heat. Now, specifically, excuse me, I didn't get much sleep last night, so I'm going to be yawning a lot today. When molecules are in the liquid phase, they can evaporate from their container. And so you've seen this in action with water all the time. So here are my water molecules on the surface of the water. And water molecules can go in any direction that they want to, bouncing off of their neighbors or the side of the container. But one of those potential directions is up. Now, not all water molecules have enough energy to do this. Only the fastest moving ones that go in the direction of the surface, excuse me, from their current position will have the opportunity to escape. So if a molecule is moving fast enough, it can break free of the attractions that are holding it to other liquid molecules and enter the gas phase, even though the temperature would dictate that the substance should be a liquid. So we'll say liquid at temperature below boiling. So some particles enter the gas phase. And we call this a vapor. I'm Canadian, so I put a U in there. I'm half Canadian, I guess. My better half. So, specifically, a vapor is a gas at a temperature that it should be a liquid. So, water vapor exists from any temperature below 100 degrees Celsius. If you go over 100 degrees Celsius, it's no longer called water vapor. Then it's steam. But below 100 degrees Celsius, it's water vapor. Now, the process by which this happens is called evaporation. So, you've seen this happen with water on the ground outside. For example, right now it's raining up here in Everett. There's water on the ground, but in a few hours after the rain has stopped, the water will have evaporated and the ground will be dry again. On a particularly warm day, this is kind of rare, but if it's quite warm out and it starts raining, you actually get like this mist along the ground because the water evaporates so quickly. And you actually get a mist of water vapor just along the surface of the ground. I don't know if you've ever seen that before. The reason that it does that is because the water evaporates quickly because the ground is really warm, but then the air around it is a little bit cooler. And then it condenses and you get this sort of like low fog at like your feet that you can walk through. It doesn't quite get that thick, but you can definitely see the evaporation. It's really cool. But that really only happens on like days that are quite warm and then like a cold front quickly moves through or something like that, which it's the Pacific Northwest. That does happen from time to time. All right, so again, that's just a description of water vapor on your screen there. I'm going to use ethanol for this example just because ethanol has a much lower boiling point and it will evaporate much more quickly for this demonstration. But what we have here in this container is we have a sample of liquid and it's connected into a flask. This is shut, but this one's open. And then right here, and it's kind of hard to see, so I'll draw it, I'll fill it in. We have what looks like a tube that has been like colored in. And the reason that's been colored in is because there is liquid mercury in this tube. Mercury is used for pressure because it's very heavy and dense. And what mercury does is when a gas pushes on one end of it, it will move. And so you can see that over here. Here's one level of the mercury, and then here's the other one. And the reason for this is because the gas inside the container is pushing the mercury in this direction. So we establish a baseline where the mercury just hangs out at whatever level it reaches. And then we let the liquid evaporate and it becomes a gas. And so as some of the particles escape into the vapor phase here, they begin to populate this container and also this tube going to this. Because gases all exhibit pressure, they can push on various things. And the result is that they push to this degree. I didn't draw that very well. Let me try that again. And this is actually where the term millimeter of mercury comes from. So you may have recalled that from the different units of pressure. We have the torr, which is also the millimeter of mercury. They're the same thing. We have the atmosphere, the pounds per square inch, etc. But for every millimeter this goes up, that's 1 torr of pressure. Now, this diagram's kind of exaggerated to be really tiny. In reality, this flask is probably like a liter big, I'm imagining. And so that tube is probably like a fair length. So that could be like 100 centimeters. That's not 100 centimeters, sorry, that would be a meter. That could be like 15, 20 centimeters, 30 centimeters, something like that. And so this pressure that is exerted by the gas is known as a vapor pressure. Every liquid at the temperature that it is liquid has a vapor pressure because all liquids have to some extent, their molecules escape the liquid phase and become a vapor. Now, the ability of the liquid to do so is going to depend on how strongly the molecules are attracted to each other in the liquid phase. For example, if you have a bunch of magnets, like those little like magnetic beads, and you sort of stick them all together like this. And so these are all stuck together because they're all magnets. And then you drop this clump on your table. Not like actually drop it from a height. You just set it on there. And the whole thing's going to stick together. Nothing is going to leave the phase where they're all attached because they're all stuck. But if I instead did the same thing with glass marbles, and I put an arrangement of marbles on the table like this, and I crammed them all together as close to each other as I could, due to like maybe the unevenness of your table or like whether it's level or not, the marbles will start to move in just various directions because there's nothing holding them there. This is more or less what's happening in a liquid. If you imagine each of the molecules in a liquid as a little tiny entity that may or may not be attracted to its neighbors, the stronger the attraction, the less likely the molecules are going to drift off and leave the liquid phase. So the main focus of today's lecture is going to be, how do we describe the forces that hold molecules together? Are they bonds? Well, they can't be bonds because we already described that molecules are independent units, right? Two water molecules are not hooked together through a bond. Otherwise, it would just be a bigger water molecule. So there must be something else going on there. So the relationship that we want to remember, and this will be important for the next section, is stronger interactions between molecules result in lower vapor pressures. I don't know why that says is. Now that I've seen that, I can't unsee it, so I have to fix it. There we go. Likewise, if the molecules do not interact with each other very strongly at all, you get the opposite result. Weaker interactions have higher vapor pressure. Now, a very important thing happens when the vapor pressure of your liquid increases to be high enough. And what do I mean by high enough? Well, I'm going to draw another picture of a beaker. If I can select the pen. There we go. And then here's my water. And here are my molecules inside. And some of them escape. And so, in other words, I have a vapor pressure pushing in this direction because that's where my molecules are going. The molecules are going up. They are going to bonk into whatever's above them. Well, what's above them is the atmosphere. That was going great until it wasn't. Let's try that again. Good enough. And the atmosphere is pushing down because it is a ton of molecules above it, all subject to gravity in that direction. Now, as you heat up a solution, the vapor pressure increases. And the reason for that is because as you add heat, your molecules start to move faster and faster and faster and faster and faster and faster. And so more of them end up leaving the liquid phase. And if you continue to add heat, the vapor pressure will get bigger and bigger and bigger and bigger until an interesting thing happens. If the vapor pressure is so large that it equals the atmospheric pressure, then the atmosphere can no longer hold the liquid in place anymore. If there's nothing holding it in place anymore, then all of the molecules then expand and the liquid becomes a gas, and we call this boiling. And that's the second time I forgot. Oh, for fuck's sake. We call this boiling. So when a liquid begins to boil, it is because its vapor pressure is the same as the pressure around it. So the temperature at which a liquid boils depends on how strongly the molecules are linked together through these intermolecular attractions. If they are hooked together strongly, the boiling point is high. For example, water is a very high boiling point relative to most molecular compounds. It boils at 100 Celsius because the molecules stick to each other extremely well. However, something like gasoline has a much lower boiling point. In the case of gasoline, the molecules don't stick to each other very well, and so it's much easier to make it boil or evaporate. Alright, and so you get boiling that way. Now, there are some interesting consequences to this behavior. If boiling is a feature of atmospheric pressure, then going to a location with more or less atmosphere should cause boiling to occur. And it totally does. For instance, if this is... So here's my sea. Here's sea level. And then we're at the... Oops, that's not what I wanted. I accidentally clicked on the zoom out button. So, oops, wrong color. And I drew that too high anyway. So here's the coast, and then we're going to go up into the mountains over here. So if I'm trying to boil my pot of water here, I am fighting against the atmospheric pressure here. But let's suppose I'm doing the same thing when I'm camping in the mountains at like 6,000 feet. Since there is less atmospheric pressure there, it's easier to boil the water. I do not need to make its vapor pressure be as high. And the end result is that the temperature at which the water boils is reduced. You may have seen this on packaging directions that say low altitude or high altitude cooking directions. And generally what it says is it just says boil for longer. The reason being, when you're boiling something, you're trying to cook the insides to an internal temperature. And the hotter the temperature is, the shorter time you need. But if you're boiling at, like, say, 92 Celsius instead of 100, then you have to cook something longer to make sure that the inside is cooked to the temperature required to kill off whatever foodborne illness or whatever it is that you're dealing with. Now, what if we were to remove all the pressure in its entirety? Well, this is what happens when we do that. Let me find this on YouTube here. I can't spell temperature. Boiling water. And there's the experiment that I... Is this the experiment that I want? No, this is not it. But I did see the one I wanted. It's this one right here. Alright, so let me capture a window here. There we go. Alright, so what we're going to do here is we're going to put water into a container and then seal it in a bell jar. So you can see right here this plate. We don't need to see this guy talking to us. We're going to put water in the container. This plate has a hole in it, and the hole is connected to a vacuum adapter. We're going to put a bell jar over it, turn on the vacuum, and we're going to remove all of the air here to lower the atmospheric pressure. So that's what this looks like. This thermometer in here is going to show the temperature of the water once whatever change we are observing occurs on it. Sorry, spraying the cat with water because she's being loud. There's the temperature of the water right now. Alright, so let's fast forward to where he puts the bell jar on. There's the vacuum pump. He's putting a grease on the end to make sure that no air can get out. And then we just have to sit back and watch to see what happens. Because this actually goes pretty quickly. So keep your eye on the thermometer, but also on the water. Because the water is the more important thing here. Oh, I guess he's taking it out the top. I thought he was taking it out of the bottom. I usually skip over all the prep stuff and just go straight to what's going on. But now, as you remove all of the air pressure on the outside, what the water feels as atmospheric pressure decreases. And eventually you notice that something happens to the water as the vacuum is allowed to take that air away. I'm just fast forwarding here. There we go. If you ever watched water boil, which you shouldn't because it will never boil, that's how that works, right? You've noticed that this is what happens at the start of boiling is you start getting little tiny bubbles, and then you get more bubbles, and then you get to this point, which is a rolling boil. So the water is boiling now, but we didn't add any heat. All we did was reduce the pressure. Now, if we didn't remove the heat, or I'm sorry, if we didn't add any heat to make it boil, the thermometer should be roughly the same temperature. And it's hard to see here. So he's going to move it. There it is. So we are boiling water at room temperature. Now, what you'll notice is that the temperature is going down as the water boils. Why might that be? Well, think back to the phase diagram for the boiling of water. We talked about it at the very start of the class. Boiling is something that requires energy to do. It's endothermic. So the energy must go into the water. Where does it come from? The thermometer. So it's lowering the temperature of the thermometer, and then by extension itself, so that the water can boil. And the water will continue to boil until either all of the available ambient energy is gone, which is incredibly unlikely, or all of the water is evaporated. So not only can we see that boiling is an exothermic process, endothermic process. It doesn't have to occur at 100 degrees Celsius like we might have thought. So that's what the boiling point of water is. It's defined as the temperature where the vapor pressure of the liquid equals the atmospheric pressure above it. Now, the normal boiling point is just whatever the boiling point is at not room temperature. The boiling point of the liquid at 1 atm pressure. So that's the most common one given because we live at 1 atm. Does it help water boil faster if you use hot water? Yeah, it does because you'd start at a higher temperature, right? If the only thing we care about is that we get water to have the same vapor pressure as the atmosphere, and increasing the temperature of it increases its vapor pressure to start. Starting it with hotter water will get you to boiling faster. But what it also does, it has dissolved stuff in your water. So if your water tastes funny, cook with cold water and then heat it all the way up to hot. All right. On the screen, I have some questions I want you to answer. I've sort of played around with the units here, so I didn't give you them in atmospheres. You can convert them to atmospheres, you can leave them in torr. It's totally up to you. I want you to tell me if liquid A has a vapor pressure of 760 torr at room temperature, will it boil? What the heck is 760 torr? You'll have to look up the relationship between torr and atmospheres in the previous section. And it is in the slides, so you can look that up, or you can look it up on Google. Liquid B has a vapor pressure of 216 torr. Will it boil at this temperature? And then for the three liquids shown below, arrange them in terms of their boiling point. Lowest boiling point to highest boiling point, if those are their vapor pressures. Again, you're going to need to do some conversions from torr to ATM or something like whichever unit you want to work with. All right. I'm going to give you about 5 or 6 minutes to do this. We'll go over the answers when I come back. All right, one more minute. We'll go over the answers here. All right, let's go over the answers here. So we got to go over here. We'll put both of these on the screen. Get rid of my crude drawing here. All right, so remember that for boiling, if the vapor pressure equals the atmospheric pressure, then boiling occurs. Okay. Well, what is atmospheric pressure in torr? Notice that I've given you all of these weird units here. So we'll turn everything into atmospheres here. So 760 torr for liquid A. And if I look up the relationship between torr and ATM, turns out that it is exactly 760. So liquid A has a vapor pressure of 1 ATM, which is equal to atmospheric pressure. So liquid A would boil. What about liquid B? Well, we can turn it into atmospheres to compare. And I didn't actually do this number, but it doesn't really matter so much because you can see right away that there's no way that this is going to be larger or equal to 1 ATM. So this vapor pressure is too low. And so the solution remains a liquid. So liquid A will boil if its vapor pressure is 760 torr at room temperature. Liquid B will not boil at room temperature because its vapor pressure is too low. I misspoke over here in the chat log when I said it doesn't, since the temperature isn't stated. It totally does state that. It says room temperature. It doesn't matter what the liquid is because the vapor pressure is based on the liquid and not what well, so whatever the liquid is, it doesn't really matter. It'll have whatever vapor pressure it does. So this just corresponds to some randomly chosen liquid. It may not even exist. All right. For the next problem, I wanted you to arrange these in order of boiling point from lowest to highest. Now, if these are their vapor pressures, Let's just turn everything into ATM here. So we've got liquid X, which is this many torr. And we'll just do the same thing we've been doing here. 335 over 760. So that's 0.441 ATM. Liquid Y is already in ATM. And then liquid Z same as the other ones. Hit the wrong button there. And we get, wait a second, that's weird. Can you go above atmospheric pressure? Turns out you can. And we'll talk about what that means in just a second. So, here, my liquids, I can arrange them from in terms of boiling point. So which one will have the highest boiling point? Which means that it is the hardest to boil. That would be the one with the lowest vapor pressure, right? So because the thing with the lowest vapor pressure means that the molecules are sticking together the most effectively. We have to heat it more to make it boil. So X will have the highest boiling point. We're arranging them from lowest to highest, of course, because... So we'll put that over here. And then we'll just arrange them for going down. So Y must be the next one. And then we have Z over here. Z must have the lowest boiling point. In fact, if all of these are at room temperature and the vapor pressure I have is above 1 atmosphere, then the boiling point for this liquid must be below room temperature. So, yeah, you can totally have a vapor pressure that's above 1 atm. If your vapor pressure is 1 atm at room temperature, it will boil. And so the boiling point must be at room temperature. If the boiling point is higher than room temperature, you won't be at 1 atm. But if the boiling point is lower than room temperature, you'll be above 1 atm. In fact, this is the premise behind how a pressure cooker works. So, what does a pressure cooker do? If I have my water in a container, it would boil at 100 degrees Celsius because that's when the atmospheric pressure equals the vapor pressure. But what if I put a lid on it and I pressurize it? So now the atmospheric pressure inside is equal to, say, 1.2 atm. Then I have to heat this up even hotter. So that my vapor pressure increases. And so instead of boiling at 100, my water will boil at like 105 or 110 whenever the vapor pressure of the water gets higher. And so this is why if you've ever used a pressure cooker, there's a release valve where as the second that you push the button, steam just comes shooting out because all of the water that's inside is well above atmospheric pressure. And it's been heated to the point where it will boil under those conditions. But the second that you open it to the regular atmosphere, the atmosphere above your water becomes 1 atm, and so it all instantly starts to turn into steam, and so it then all gets released really quickly. And so you have to be very careful when using a pressure cooker that you don't accidentally steam yourself in the face, or that you assemble it correctly so that you don't like make a weak point where the unit can explode. Like today, pressure cookers are very safe, but I can imagine like early pressure cookers that was probably a thing that happened all the time. All right, so that's all about boiling. And there's the homework practice for that section, 85 through 90. When we come back from our break here in a second, we're going to continue with intermolecular forces, which might be the end of the unit today if we can finish that. So, oops, wrong button there. So I'm going to go get the music back. I'll start the timer, and I'll see you in about 10 minutes after the break. Hi everybody, welcome back. Oh, the second I start talking, my cat is just like, meow? Are you talking to me? No. No, I'm not talking to you. Now he's looking at me like, why not? Why are you not talking to me? Huh, I'm not talking to you. He's a good cat, but he is a loud cat. Alright, so the last section of Chapter 7 is an explanation of these forces that we have alluded to the entirety of the chapter. What are the forces that hold molecules together, and through what magnitude? So, how strong are they? How weak are they? Are there different types and flavors? All those questions and more answered now. So, an intermolecular force is an attraction between any two molecules that does not constitute a bond. Now, I've put some numbers on the screen here. And these numbers are meant to represent how strong a bond is, or interaction. So I'm highlighting the numbers and what the interaction is shown as. The number is just a reflection of how powerful, and you don't need to know what the units are, kilojoules per mole, but the number is just a reflection of how powerful the bond is between those two atoms. So in HCl, the hydrogen and the chlorine are bonded together by sharing their electrons through a covalent bond, and it has a strength of 431. The attraction between the two molecules, however, is much weaker. Its strength is only 16. So if I was going to add heat to this molecule, I would break the weakest interaction first, and that would be this one. So if I had these molecules moving around in my container, and I started to heat them up, I would not break the HCl bonds. These are strong and would hold together. But the intermolecular force is much weaker. And so we break that intermolecular force when we heat it. So when you heat water, water follows the same principle. So here's my water. And so it has bonds, and those bonds are strong. But it also has interactions between other molecules, and relatively speaking, these are weak. So when I boil my water by heating it up, this is the first to go to turn these water molecules into gaseous molecules. So when you are heating your water and you observe steam, steam is actually water vapor. It's not just a collection of H's and O's randomly, because that would be actually very dangerous. Hydrogen is explosive and oxygen is explosive, and if you started boiling water over your burner, you'd create a bomb. Every time you boiled water, if you were dissociating everything into hydrogen and oxygen, it would all go up in flames. But that doesn't happen. Water vapor is not flammable at all. It's very stable. So these interactions between molecules are what we call intermolecular forces. An intermolecular force is a force of attraction between two molecules. And whenever we draw intermolecular forces, we always use dotted lines. Don't use a solid line. Solid lines are for bonds. Dotted lines are for intermolecular forces. Now, why are these interactions weaker? There's two features that occur. One of them is charge. In compounds that have charges, the effects of attraction are strong. But in molecules that we don't have charges anywhere, right? The electrons are shared between atoms and no electrons are transferred between the two atoms. So we don't make an ionic compound in things like HCl or H2O. But, as we talked about, excuse me, in a previous chapter, molecules can be polar. And if molecules are polar, like HCl is, that's the wrong pen. There we go. If molecules are polar, these two things could be attracted to each other. So charge does come into play here, even though no ions are present. If things are polar, they will stick to each other. And if things are small, then the distance between them tends to be small too, and they will stick more strongly. Distance is definitely a factor for attractive forces. If you have ever had something magnetic on your fridge, you may notice that the attraction between the magnet and the fridge only exists if the magnet is relatively close to the fridge, right? If you hold the magnet like a centimeter over the surface, you can feel it pulling the magnet towards the center, or towards the fridge. But if you hold it 5 centimeters away, or 10 or whatever, the magnet doesn't see the fridge anymore. It's too far away. So closer also improves the magnitude of the intermolecular forces. And the only way to get things to be close enough is to make them really tiny. Now, boiling point and melting point are both affected by intermolecular forces. And so what that means is that, as we discussed in the previous section, if the intermolecular forces between molecules are strong, the boiling point needs to be very high in order to overcome them. If the intermolecular forces are weak, then the boiling point can be rather low to overcome them. So as an example here, I have HCl with negative 85 degrees Celsius as its boiling point, and H2O, which boils at 100 degrees Celsius. Which has stronger intermolecular forces between the molecules? Well, which one is harder to force into the gas state? And looking at the boiling points, you can see that, oh, well, water is way, way, way higher. So it must have the stronger intermolecular forces. I have to overcome those by heating it much higher than I have to heat HCl. Now, why is that? What specific feature of water does this that HCl doesn't? And what other features are there that we can account for so that we can make predictions about things that will boil and their temperatures? And so that's what we're going to be doing right now. Once I pet the cat and then tell her to go away. Go away. Go away. All right. So, like I just mentioned with our HCl with the picture of the partial positive and partial negative, anything that is polar will try and align such that opposite polarities will interact. Now, all of these are delta. These are all partial. But they didn't want to keep writing that symbol over and over again, I guess. So, on the left in diagram A, I have a bunch of liquid molecules that are all just kind of floating around. And you'll notice that all the positive sides are lined up in such a way that they are adjacent to negatives and are as far apart from other positives as they can be. Even though the molecules are not lined up, excuse me, they're not lined up regularly, they still do the best they can. They're trying their best, you guys. And as the molecules move past each other, they then bend and twist and change their orientation such that they try and maximize all of the attractions and minimize their repulsions. Any attraction between a partial charge, partial negative and partial positive, is called a dipole-dipole interaction. That's the worst color I could have picked. Let's try that again. Oh, when I have the... I swear, PowerPoint, you're going to be the death of me. There we go. Dipole-dipole interactions. That's what these are called. Something has a dipole if it is polar. And so you'll have to remember back to Unit 5 where we drew all the Lewis structures of everything. And then I asked you, is it polar, yes or no? So now I'm going to give you molecules. You'll have to go back and draw their Lewis structure again, predict whether they're polar, and then predict the intermolecular force that is present in that molecule. If it's polar, it'll have one type of force, the dipole-dipole force. If it's non-polar, we'll have something different, which we'll talk about later. And then there's a special condition of the dipole force that's extra strong, which, guess what molecule has that? It must be water, right? Water has a really high boiling point. It's totally water. Now, the more polar something is, the higher its dipole moment. And what this means is the higher electronegativity difference. So remember that we can calculate delta En. The sharper the differences in electronegativity on the molecule, or for all the bonds on the molecule, and depending on their orientation in space, provided they don't all cancel each other out, the stronger these dipole-dipole forces will be, and the stronger the interaction. As dipole moments go up, boiling points go up as well. So I believe I have a picture. Oh, no, I guess I don't. That's okay. Now, as molecules get smaller, the molecules are able to get closer and closer and closer together without bonking into each other. A large molecule might have other parts of the molecule that would spin and twist and would not allow other molecules to get quite as close because it's harder to fit them together as molecules get big, because all the bonds are rotating and stretching and doing stuff like that. But a tinier molecule has fewer obstructions in the way, and thus it can get closer to other molecules and will have stronger dipole-dipole forces. So we're going to make a chart here to sort of categorize our intermolecular forces. All right, so that's going to look kind of like this. So on the y-axis, I'm going to write strength of intermolecular force. And as the strength goes up, so does the boiling point, and so on and so forth. Now, dipole forces are quite strong. However, as the size of the molecule increases, they tend to become less effective. So on the y-axis, we're going to write size of molecule. And the rubric that we're going to be using is molar mass. So something that's 20 grams per mole will be a small molecule, whereas something that's 2,000 grams per mole would be a very large molecule. All right. So we'll come back to that. Let's go to the next example, which is the hydrogen bond. Hydrogen bonding is just a special type of dipole-dipole. On this molecule right here for oxygen and hydrogen, they have a very polar bond. The difference in electronegativity here is quite large. So hydrogen has electronegativity of 2.1. Oxygen is 3.5. That is a significant difference. Remember that between 0.5 and 2, we have polar covalent. Because that is such a strong difference, those delta pluses and delta minuses are considerably larger than they would be for other pairs of atoms. And water is so tiny that this distance is small, which means that I can allow this delta plus and the delta minus on oxygen here to get right up next to each other to form a strong interaction. And this is specifically called a hydrogen bond. Now, in order to make a hydrogen bond, you need a series of things. And the things that you need are, hydrogen, right? But hydrogen must be bonded covalently to an atom that has a very high electronegativity. There are only 3 candidates, and those 3 candidates are nitrogen, oxygen, or fluorine. So you can see in all of these cases right here, here I have a hydrogen covalently bonded to nitrogen, here it's bonded to oxygen, here it's bonded to hydrogen. Doesn't matter which of those 3, as long as it's one of those 3, you can qualify for a hydrogen bond, but you need a second condition too. And that condition is that our hydrogen must be pointed at the electron pair on another nitrogen, oxygen, or fluorine. And I have that going on here too. I just drew over it, unfortunately. If you meet these 2 conditions, your molecules have hydrogen bonding. Now, hydrogen bonding can occur between 2 molecules whether they are the same or whether they are different. That doesn't matter. The molecules involved are irrelevant. All we care about is that there is a hydrogen that is covalently bonded to a nitrogen, oxygen, or fluorine, and that we can point that hydrogen to the electron pair on another nitrogen, oxygen, or fluorine in another molecule. If we do that, they will stick together much more effectively than a dipole, and the boiling point goes way higher than you would predict. Now, if I ask you where's the hydrogen bond, what you would do is you would circle all 3 atoms involved in the hydrogen bond. So both the H with its covalent bonded partner and the NO or F that the H is pointed at its electron pair. So there are our hydrogen bonds right there. Now, is it a bond? No, it's an intermolecular force. Remember that intermolecular forces are not bonds. Which is super confusing. Why would you call it a hydrogen bond? Because chemists suck. That's why. So you just have to remember a hydrogen bond is an intermolecular force that is just extra strong. It is not actually a bond. All right, let's look at the impact on hydrogen bonding and structure. So first off, what I want you to try and do for this example is I want you to draw the Lewis structure of these 4 molecules. That means going back to Unit 5 and reviewing how to do Lewis structures if you don't remember how to do that. Hopefully you do. Draw the Lewis structure of these 4 molecules here. The central atom is listed first, unless that atom is not able to do that, such as hydrogen. Draw the Lewis structures for these 4 molecules, and then try looking at them, see if you can make them hydrogen bond with another copy of themselves. So for instance, if you had 2 CH4 molecules, is there anything you can do to make them hydrogen bond? Can you do that with 2 H2N and H2s? And so on and so forth. We'll go over the answers in just a second. All right, hopefully everybody's drawn a Lewis structure by now. So what we're going to do, I'm going to scroll my screen down a little bit here. Oops, I need to actually have the molecules on the screen. So what we're going to do is we're going to draw the Lewis structure of all of these. Now, you can actually save yourself some work. And not actually have to draw the Lewis structure by realizing, oh, there aren't N's, O's, or F's in here, so this can never hydrogen bond. Because these atoms are required, so that immediately eliminates CH4. And for the same reason, H2S is also excluded, because they can never form hydrogen bonds, right? They don't have any N's, O's, or F's in them, so these guys are out. Now, what about CH3F? Oh, I skipped over H2N and H2. I'll just do CH3F because it's smaller. If you draw the Lewis structure for CH3F, this is what you get. So what we're going to do is we're going to do this. That's not what I'm going to do. I tried to draw a box around it. It didn't work. So we'll do this. And we'll go up here to copy. And then paste. I'm going to make another one here. And now my goal is I'm going to try and spin this around somehow so that I can get an H between an F. But you'll notice that there's an issue here. There's no H directly bonded to my F, so no matter what I do, I'm never going to have a hydrogen bond, right? Because this goes FHOC, but C doesn't count. I have to have NO or F in this position. So this cannot hydrogen bond. Because there is no hydrogen that is covalently bonded directly to an NO or an F. So these three molecules, you can't make hydrogen bonds between. So what we're going to do, oops, I got to go down to this layer. Let's look at H2N and H2. So I'm going to draw that Lewis structure. And then what I'm going to do is I'm going to copy and paste it. So copy, paste. And then I'm going to try and rotate it around so that I can make this work out where I have my hydrogen, one of these hydrogens pointed at the electron pair on the nitrogen. So if I do this, then I have my hydrogen is covalently bonded, to a nitrogen, and I'm pointing it at the electron pair on another nitrogen. So this would be a hydrogen bond. Now, you could pick any other orientation you want to. I could use any of the H's connected to any of the N's to make a hydrogen bond. So the only one that is capable of hydrogen bonding here is H2N and H2. All right. For the next question here, we'll draw how ammonia can hydrogen bond with water. So I gotta clear these, and I don't know what's on layer 1, actually. Nothing. That's okay. So let's get rid of this. That's not how we get rid of that. I got to circle with this tool. Boop, there we go. And you know what we're going to do? We're going to just, we'll come back to that. I'll just turn it off so they can't see it, and now we can draw wherever we want to. All right, so let's draw ammonia. So we'll draw the Lewis structure of ammonia. That's pretty straightforward. And then we'll draw the Lewis structure of water. All right. Can these two hydrogen bond? I'm going to give you a second to just kind of visualize them in your head. Spin them around however you want to. Try drawing a hydrogen bond on your paper, and then try drawing a hydrogen bond using the other orientation of the molecule. So if you used ammonia to form the hydrogen bond with its covalent bond, try doing that same thing with water. Can you do it forwards and backwards? I'll give you a second to look at it. All right, so we're going to spin these around. So I'm going to go, whoop, didn't do what I wanted. We're going to like this. And then I should be able to do this to it. All right, so can I move it? Yeah, I can. I can totally move it wherever I want to. So what I'm going to do is I'm going to line this up such that the NH bond points at the electron pair on my O. So we're going to go like that. Boop. There we go. And then we have the hydrogen bond right there. It didn't write because I didn't hit the button. There we go. So I can make a hydrogen bond right here. Because my hydrogen is covalently bonded to an N, and it is pointed at the electron pair of an O. Now, in this case, ammonia here is donating the hydrogen to form the bond. So we would call this a hydrogen bond donor. And here, water is providing the electron pair to accept the hydrogen pointed towards it. And so we would call it an H-bond acceptor. And these are terms that you might hear thrown about. Some molecules can be both donors and acceptors, but in some cases, some molecules can only do one or another. This is going to be really important when we get to Unit 8. For example, acetone is a great hydrogen bond acceptor. However, there is no configuration of atoms that allow it to be a donor. So it will interact strongly with things that can form hydrogen bonds to it, such as water. But it itself does not interact as strongly with other molecules of its kind because it can't hydrogen bond. All right, so now we'll clear all that out. Oh, you can't see it. Oh, shoot. Yeah, that's a problem. There you go. Sorry about that. What is NH3 again? NH3 is ammonia. Oh, it's the hydrogen bond donor. I'm sorry. Yeah, because the text was hidden, wasn't it? Sorry about that. Okay. You can go ahead and pause the video if you need to write it down. I'm going to draw the molecules again. There we go. And now what I'm going to do is I'm going to try and make this one over here hydrogen bond to the water. So last time I did something like this to make my bond, but what if instead I did this? Now water is the hydrogen bond donor. And nitrogen or ammonia is the hydrogen bond acceptor. So there would be my hydrogen bond. My hydrogen is attached to water, so this is the H bond donor. And this would be the H bond acceptor. So these molecules can go in both orientations. One could be the donor, one could be the acceptor, but that is not universally true. HF and HCl cannot hydrogen bond because even though I have HF here, I have to point it at an electron pair on the other molecule, and this is not NO or F. So hydrogen bonding does not occur between HF and HCl. They would just mix together. All right, so that's hydrogen bonding. On this chart, I have the effects of hydrogen bonding. You can see that, so this is molecular weight versus temperature. And you can see that as things get bigger, their boiling point tends to increase kind of linearly, right? Now, that should be a universal trend, and that should apply to water too. So this is the boiling point of where water should be if it did not hydrogen bond. But because of hydrogen bonding, the boiling point skyrockets up 200 degrees Celsius. Can you imagine taking a shower in the morning if it was negative 150 Celsius? Like, life wouldn't even be possible. It's because of hydrogen bonding and this phenomenon that, like, we can even have liquid water to begin with, and that life can flourish. So, hydrogen bonding is very, very strong, which means that we need to go and add it to our diagram. So, we'll go like this. We'll get rid of what was on the screen here, and we'll turn this back on. Boop. So, this color will be hydrogen bonding. Hydrogen bonding is the strongest intermolecular force that we're going to talk about for a small molecule. But as molecules get bigger, just like any other dipole force, these become less effective. Oops. It's not supposed to go through the line. It's supposed to just go on top of it. So the magnitude of how good hydrogen bonds are also depends on sizes. Things that are tiny, like water, super good at hydrogen bonding. Things that are huge, not as effective, but still good. All right, so we can now identify visually dipole-dipole interactions by looking at differences in electronegativity, and also hydrogen bonding by just looking at the molecule. What happens? Oh, this is just a structure of what ice looks like. So ice forms by making hydrogen bonds, and you get these little hexagonal arrangements of water molecules, where a hydrogen is pointed towards an oxygen that is neighboring it. Which is really cool. What happens for an intermolecular force if none of these things are present? You don't have a polar bond. You don't have a hydrogen bond, certainly. What options are available? Is there anything that makes molecules stick together? And it turns out that there actually is a mechanism by which molecules can stick to each other if they don't have dipoles. Because every atom has electrons. Even if the atoms or the molecules are completely neutral, they have no dipole at all, they still have electrons. And electrons have a very basic interaction. They interact with the nucleus, whether it belongs to their atom or someone else's. Charge doesn't care. There's no ownership in charge. A negative will be attracted to a positive regardless of where the positive is. And as a result, if you get a random distribution of your electrons, so like let's say that this electron was just over here for a while, then most of my electrons are on this side, and there's nothing on this side, so these electrons over here would be attracted to it, thus holding the molecule together. And I have this really terrible picture here that I need to replace this picture, but if most of your electrons are on one side of the molecule, they will be attracted to the nucleus of an atom that is further, or that has fewer electrons on it. So what ends up happening in this circumstance here is that when you randomly distribute your electrons, sometimes they shuffle off to the side. That creates a temporary dipole. However, it is a dipole and it functions like any other dipole. It's just temporary. And because it's temporary, it only lasts for a little while and thus is weaker. So we call this the London dispersion force. You may actually just see it called the dispersion force. But the London force arises from the instantaneous unequal distribution of electrons around a molecule that is nonpolar. Now, all molecules have electrons, so all molecules can do dispersion. Now, how easily can molecules do dispersion? It depends on this factor here. This is called polarizability. Things are more polarizable if they have more electrons. What are the odds of you having an uneven distribution of electrons when you only have 2 electrons? Well, you'd have to have both on the same side and electrons repel, so that's rough. But what if you had 20 electrons? Well, now I just need one more to be on this side than the other side. That's way more likely. So the number of electrons affects how polarizable a molecule is. More electrons equals stronger dispersion. What else affects dispersion? The shape of the molecule matters a lot too. So if I go down here and draw some pictures here, molecules have dispersion forces over their surface area. So if I draw CH4 like this, the surface of the molecule is roughly spherical because the molecule occupies a tetrahedron. If I bonked it into another CH4, they would only see each other where the spheres interact. Now, what if I took a longer molecule like this? So this is pentane. And there's its Lewis structure. And if I draw a shape around it, it's kind of like an oblong ellipse or a hot dog or something like that. If I took another molecule of that, where could it interact? Well, it could interact all in here, right? Anywhere it can contact, I can form dispersion. So if I have a molecule that has a bigger and longer surface area, it will have stronger intermolecular forces through dispersion. Now, the only way to really know what the surface area of a molecule is to eyeball it. If you can draw the molecule and it looks longer and like more cylindrical, then you can do this sort of thing where you just line them up end to end. In biochemistry, if you're going to take Chem 131, you're going to learn about lipids. Lipids are really, really, really long molecules. They're like these carbon chains that are between 12 and 20 carbons long. So I drew 5. Imagine a molecule 4 times as long. It'd just go in a straight line, and you could line them right up with each other. And that's a good thing, because lipids tend to stick together. This is why stuff like margarine or butter are solids at room temperature, because we can make the lipids stick together. All right. So, oops, that's the wrong slide there. We're going to go to that in just a second here. So in our discussion of dispersion forces, we can look at individual atoms or entire molecules. For example, if I look at xenon versus neon, xenon atoms have lots and lots and lots and lots and lots of electrons. In fact, a xenon atom has 54 electrons. A neon atom only has 10 electrons. So xenon is going to be more easily polarized. Because it has more electrons. And therefore will have stronger dispersion forces. And if it has stronger intermolecular forces, of which dispersion is one of them, it'll have a higher boiling point. So between xenon and neon, xenon has a much higher boiling point. They're still both relatively low. Like xenon boils at room temperature or below, but neon boils way below room temperature. Now, what if the molecules that you're looking at have the same formula but different shape? Is that possible? Yeah, it's totally possible. On the screen here, I have neopentane and N-pentane. So, neopentane is just this, where my carbons are in a sort of circular arrangement or a cross. And then pentane I drew on the other screen, where my carbons are in a row, like this, and all the H's around it. They both have the formula C5H12. You can count all the C's and the H's on the right there. However, their surface area is very different. For pentane, we have the long oblong shape. And for neopentane, we have a circular shape. So these two molecules can line up and interact with each other along their lengthwise axis. But these two right here can only interact with each other wherever the spheres bonk into each other. The difference in these for their boiling point is shown below. Neopentane has a boiling point that is 20 degrees or so, 25 degrees lower than N-pentane. So just changing the shape changes the boiling point by 25 degrees Celsius. Remember, Kelvin and Celsius are the same thing. 1 for 1. And that's kind of surprising that just changing the structure changes the physical properties like that. So, all right. Now, because all matter can do this, the number of electrons matters, and we correlate the number of electrons with molar mass. And because these are temporary, usually dispersion forces are the weakest. So let's go add that to our diagram, and we'll show when the usually kicks in here. Now, dispersion just gets better and better and better the bigger the molecule is. But it starts off weak when there aren't that many electrons. So it starts off weak, and then it tends to do this. Whereas the other ones depend on just a polarity of the molecule. And that polarity is harder and harder and harder to make a significant part of the molecule if the molecule gets bigger. Dispersion is just how big the molecule is. So dispersion gets better and better and better, and if you make the molecule big enough, dispersion is the winner. For large molecules, again, like lipids, which we're going to study in biochem, the molar mass of those molecules is so high that dispersion is by far the most important force. So even though it's very, very wimpy for a small molecule, for a large molecule, it is extremely significant. All right, that's our summary on intermolecular forces. So the three intermolecular forces are hydrogen bonding, which is the strongest, dipole-dipole, which is fairly strong, and then dispersion, which is weak. Those are all for small molecules, which we'll just put this back up here on the screen here. But as molecules get bigger, dispersion tends to get better and better and better until it's the best, and dipole-dipole and hydrogen bonding get weaker and weaker and weaker. All right. So looking at these two molecules, what you can do, and we're kind of out of time for today, unfortunately, so we'll have to finish this unit tomorrow. What we can do is we can consider which molecule has the stronger dipole forces and which one has the stronger dispersion forces. So in order to distinguish between these, we want to look at polarity of each molecule. I wrote the wrong thing. There we go. All right. So F is the most electronegative atom. So this is going to be very polar in this direction. Whereas I is not very polar at all. And so there's actually going to be very little dipole in here. I'm not even going to bother writing it. All right. Now, which has the stronger dispersion forces here? Well, dispersion forces care about molar mass because that leads to more electrons, right? If you know the molar mass of something, you can compare any two things. And the one with the molar mass must have more electrons in it. So, looking at CH3I, I get roughly 141.9 grams per mole. Typing it into Lentech, which I'm actually just doing it on the calculator real quick. But if I look at CH3F, I only get 34.0 grams per mole. This is way bigger, so there must be way more electrons here. Which means stronger dispersion forces. Now, what about which one has the higher boiling point? It turns out that it's very difficult to compare boiling point when you're looking at dipole versus dispersion if the masses are very different, because when I go back to that chart that we have here, where does the crossover point actually happen? Like, where does that happen with regards to size? And the answer is that's kind of arbitrary. It's hard to really define that. So what I'm going to do is I'm going to tell you small molecules or big molecules and not give you something that might fall in the middle, because I think in this case, I think this molecule for CH3I actually is the higher boiling point. But there's no way that you would know that. All right. Can we finish this slide before we go? Yeah, so there we go. All right. So here's our summary of intermolecular forces. For small molecules, dipole and hydrogen bonds are the most powerful. Dispersion are very weak when they are in a small molecule. When they are in a large molecule, dispersion are the most significant force. All of these are interactions between molecules that cause them to stick together. The stronger the molecules stick together, the higher their boiling point ends up. All right, I think this is the last slide, so I'm going to just put all this on the board here. I'm going to leave these exercises for you to do as practice. If you have any questions, you can email me about them in the Discord channel or my email. But that's chapter 7, I believe. Hooray! We got to get our music here. All right. And that's really all the time we have for today. I do want to thank everyone for coming out to the lecture. I will be putting the quiz for Unit 7 online. So let's add that to this. So quiz number 7 due Monday, which will be... Oh, no, not Monday. That's a holiday. Can't do that. So it'll be due Tuesday instead. I'm not going to make something due on Memorial Day. That's dumb. And then also... So there will be an extra lecture tomorrow. Tomorrow being the 25th, so Tuesday. Normally we don't meet on Tuesday, but I would like to just make sure that we can get through all of the content. So if we do a lecture on Tuesday and also on Wednesday this week, then we're going to be probably well ahead, and we might even finish the material early, which means more review time at the end, because there is an exam at the end of week 2, and there's a final during finals week, so there's lots of tests and stuff coming up. And we want to just try and stay on top of the material. chapters 8 and 9 are not super long, and that's great news for us because chapter 10 is a little bit more intensive. It's a little bit more difficult. Chapter 10 is acids and bases, which is really important because pH is a very important concept, especially if you're going to be working as a nurse. Knowing what blood pH is very important. But yeah, so please join us tomorrow for a lecture. If you can't make it, that's okay. The recording will be posted to YouTube, and it'll be available in the playlist for whenever you can watch it. Yeah, I don't have anything else to say, so hooray. We'll call it a day here, and I will see you tomorrow for Chapter 8. Make sure to get quiz number 6 done. It is due tonight. Take care.